So the very last concept we're going to be looking at in this unit is actually, it has nothing to do with acids and bases. In fact, what it's going to be working with is specifically the dissociation of ionic compounds in solution. And looking at the reason why I put it in this unit is because we're going to be using your equilibrium constant instead of Ka or Kb or Kc or Kp. We've got one last solubility product, and that is your KSP. Now, your KSP simply tells you how soluble the solid is in water. So the larger your KSP, the more soluble the solid was in water. Because remember, if your KSP is large, that means that your products are favored. Now, we have to make sure that we distinguish between solubility and KSP because they are not actually the same thing. Solubility is simply the quantity of solute that dissolved in your solvent, while your KSP is your equilibrium constant for the equilibrium between your ionic solid and the saturated solution. Saturated solution meaning those ions that dissociated from the ionic solid. And so what we've got to do in order to write the equilibrium expression for the dissociation of an ionic compound, we first have to write out the chemical reaction first. And so, for example, if I gave you calcium fluoride, which is CaF2, that would dissociate into its ions. So the ions would be calcium with a 2+ charge and 2 fluorines. So that part isn't new. And in fact, none of this is really going to be super new. It's just going to be applying everything you've learned to this new concept. So that is the dissociation of calcium fluoride, that ionic compound. And to write the equilibrium expression, remember, we're going to consider the concentrations of the calcium ion, the fluoride ion, but not calcium fluoride because it is a solid. And so your KSP would be this: calcium ions, the concentration of calcium ions, times the concentration of fluoride ions squared. And that's your KSP. Okay, so you've got a couple of practice problems in your notes, so pause this video and then we'll move on. What we're going to look at in this section, there are 3 different factors that can affect the solubility of an ionic compound, basically its ability to dissociate into its ions. And the first one is one we've actually already looked at, the common ion effect. And so just as a review, the common ion effect tells us that the solubility of a slightly soluble salt is going to decrease if there is a second solute present that has a common ion. And so we actually already looked at this in this unit, but let's look at an example to make sure we're clear. So if I give you lead 2 chloride dissociating into its 2 ions, lead ion and the chloride ions, if I were to add HCl to the system, what's actually being added that I care about is that chloride ion, because notice I have chloride in my products for this. And so chloride's being added, and so that's going to cause a shift, and remember this goes back to the previous unit with equilibrium, it's going to cause a shift to the left because I've increased my concentration of chloride ions. So the shift is going to be to the left, and so if you think about the solubility of PbCl2, if you've shifted to the left, that means lead chloride is going to be less soluble, so the solubility is going to decrease. If it had shifted to the right, then the solubility would have increased. So that's one factor that affects solubility. The second factor is pH. Okay? So if we look at, for example, magnesium hydroxide dissociating into its ions, if I were to go ahead and I were to add sodium hydroxide, in your mind you should be thinking, well, hydroxide is the ion that, this is basically a common ion effect problem. Hydroxide is what's being added, and so that's going to cause the hydroxide ions in my products to increase, which means I'm going to shift to the left. All right? If I shift to the left, that means that the solubility of magnesium hydroxide is going to decrease. This seems like I just repeated myself from the previous section. However, what I'm talking about is pH. So in this case, I increased the pH by adding sodium hydroxide, which then caused a shift to the left, which caused my solubility to decrease. Sodium hydroxide was added, so since that's a common ion, that means that the salt's going to be less soluble. Well, what if I don't add a common ion? What if instead I add hydrochloric acid, for example? Well, that isn't an ion in that dissociation reaction. However, what you should notice is that I'm adding H+. Well, H+ is going to react with hydroxide, which we learned in this unit, and it's going to form water, which means the concentration of hydroxide ions is going to decrease, which means you're going to have a shift to the right. And if you shift to the right, that means your solubility is going to increase. So the second rule here is if you add an ion that's going to remove one of the ions in solution, then the solubility is going to increase. So the only new term here, this is Le Chatelier's principle. The only new concept is this concept of solubility. So if it's shifting to the right, that means that the ionic compound is going to be more soluble. If it shifts to the left, it is less soluble. All right, so the third concept we're going to go over, the third way that you can change or alter your solubility, is by forming a complex ion. Now, in order to understand what a complex ion is, I've got to really quickly go over the last type of acid base that can exist, and those are Lewis acid bases. And Lewis acid bases are not that commonly addressed in problems, and that's why I'm just going through it quickly. It's just one new definition. So a Lewis acid is an electron pair acceptor. Notice that's the exact opposite of what a Bronsted-Lowry acid is, because that is a proton donator. So Lewis acids are an electron pair acceptor, while Lewis bases are an electron pair donor. Okay? What exactly does that mean, though? If you look at this, in this example, ammonia is going to donate its 2 electrons to boron, okay, and create that full compound. Now notice, since nitrogen donated its electrons, that makes it a Lewis base, while since boron accepted them, that makes it the Lewis acid. Well, this seems really out of place, but it's not. It's going to help us in order to understand what a complex ion is. So this third way of altering the solubility of an ionic solid is if a complex ion is formed. So what you should notice is that the first reaction, 17.21, you've got silver chloride, and it's going to break apart into silver ions and chloride ions. Now, if you were to add ammonia to that reaction, what happens is ammonia is going to form a complex ion. That's AgNH3, 2 with a +1 charge. Notice that, just to understand where this came from, typically the NH3, whatever you're adding, it's going to have double the number of what the charge of that metal was. So for example, here Ag has a +1 charge, so ammonia, there are going to be 2 of them. Notice ammonia doesn't have a charge, so that complex ion keeps its +1 charge. So that's where that comes from. What you should be really focusing on is the fact that I removed silver from the products. And so since I removed silver from the products, that means that it's going to increase the solubility of AgCl because I removed silver by creating that complex ion. So for all 3 of these ways that I can change the solubility, what I'm doing is I'm either adding or removing product in order to cause the equilibrium to shift to the right or to shift to the left. So not something that's really new, but it is in the sense of solubility. All right, so there's one last key concept for us to go over, and that's the precipitation and separation of ions. And we're going to be using your solubility constant in order to determine whether or not something is soluble or not. So in order to determine if it's going to precipitate, we're going to use the reaction quotient. That was your Q from last unit. Okay, so here are the rules. If your Q is greater than your KSP, that means that the concentration of products is too large, and therefore your reaction needs to shift to the left in order to reduce your Q, meaning that you're going to be forming solid. You're going to be forming a precipitate. You're going to be shifting to the left. If your Q equals your KSP, then your equilibrium already exists. And if your Q is less than KSP, that means you need more product, so your solid is going to dissolve until your Q can be equal to your KSP. And so for these problems, I'm going to first solve for Q compared to my KSP and determine, okay, is some of my solid going to dissolve or is more solid going to be formed? So for example here, it tells me that I have sodium fluoride and it's going to be mixed with calcium nitrate. And so what we need to keep in mind before we even start this problem is by mixing sodium fluoride and calcium nitrate, the precipitate that could possibly form, is calcium fluoride. And so I'm going to write the dissociation reaction for calcium fluoride. So CaF2 is going to dissociate into calcium ions and fluoride ions. And the reason why we ignore sodium and nitrate is because they're not insoluble at all. We can only use ionic compounds that are slightly soluble, like calcium fluoride. So I've got calcium fluoride, and so what I need to do is I need to calculate the concentration of calcium ions and the concentration of fluoride ions, and then I'm going to plug that in to my reaction quotient formula. So those are my concentrations that I found. Remember, you need to take the volume, so 0.050 of the fluoride ion, multiply it by its concentration, and then divide by the total volume, which would be 0.06. So that from the previous homework is going to come back and get you if you didn't learn how to do that, so make sure you're comfortable with those concentrations. So my reaction quotient is equal to my concentration of calcium times my concentration of fluoride ions squared. And so I'm going to plug in my values, which I did up there, and I get for my Q 4.65 times 10 to the negative 7th. Well, since my KSP is 3.9 times 10 to the negative 11th, that means that my Q is larger than my K, which means I need it to shift to the left in order to decrease my Q, which means that a precipitate, a solid, is going to be formed. And so that's one type of problem that you can be given in which you need to determine whether or not a precipitate is going to be formed. The other type of problem is in which you are given two different ions and you're asked which one is going to precipitate out first. And so that's called selective precipitation, in which you can precipitate out one ion first and then the second ion based on the work we're about to do. So ions can be separated based on the solubilities of their salts, and if we separate them using a reagent that's going to form a precipitate with it, it's called selective precipitation. So if we look at this problem, we're given magnesium ions and copper ions. All right. It asks which ion is going to precipitate out first with hydroxide. So what we need to do is we need to calculate the concentration of OH that's needed to precipitate out each of these cations. And the one that requires the least amount of hydroxide, that's the one that's going to precipitate out first, because as I slowly add hydroxide, one will precipitate out before the other one will. So I'm going to first work with magnesium hydroxide, and there is my dissociation reaction right there, and I'm going to calculate my Q. So I've got my KSP 1.8 times 10 to the negative 11th. That's equal to the concentration of magnesium ions times the concentration of hydroxide squared. And so when I do this, I find that my hydroxide is equal to 1.9 times 10 to the negative 5th. When I do the exact same thing for copper hydroxide and plug that in, what I get for my concentration of hydroxide is 9.8 times 10 to the negative 5th. So copper hydroxide, you need less hydroxide in order to start precipitating out copper hydroxide. So because you need less hydroxide, that means that the copper hydroxide is going to precipitate out before magnesium hydroxide.